Start recording. All right, folks. Well, let's get started for another day. So first, Chris and I graded your midterm, and we left them in my office. So I have homework for Chris, which is, yeah. So here's the key to my office. They're sitting on the round table, where we just were. Sorry about that. It's probably the only reason you guys are here. Beyond that, let's see. So you're continuing to work on your homework. When is your homework due? 2 weeks from now? Yeah, so plenty of time. Cool. That's about it. So we graded the exams, had like an interesting flat distribution on the range from 0 to 110, which is fascinating statistically. I guess this is what happens with small numbers. I'm going to open the windows, by the way. That's fine. So obviously our goal here is not to penalize students for taking a hard exam. So here's what I propose. With the next homework, if you would like for extra credit, essentially what you can do is take the exam over as much time as you want. Like just write up nicer solutions to the exam problems, and we'll basically give you some extra credit to go along with that homework, just to make sure that you understand the answers to all the problems on the exam. I think it's a good way as any to help you guys study for the final and get over. I feel like every time, like I remember in college when I took like exams and I did badly, then I would like feel some weird hatred toward them and then never look at them again. But the reality is, you might as well go back and learn something. So anyway, that's our goal here. Really, my goal is to give you guys all as high grades as possible, and this is one way that I can think of doing that. Does that sound good? Excellent. The other thing I noticed is that there is zero correlation between the students that were acting really uncertain in my office hours about whether they're good at this or not, and the ones that did well or not. So I don't know what to make of that, other than apparently we're all bad at introspection. In any event, that's our basic setup. So the rest of this class procedurally is straightforward, right? There's 1.5 more homeworks and a final. That's it. Cool. Okay. So with that, today we continue our exposition of the conjugate gradient method, or as my undergrad professor put it, the conjugate gradient method. But don't repeat that, and don't tell him I said that. But in any event, the conjugate gradient algorithm is our newest and latest and greatest algorithm for solving linear systems of equations, at least when the matrix is positive definite, right? In particular, what did we do in CG? Well, the very first thing we did, we're going to have like a 2-minute review of the previous lecture, and then we'll continue our exposition from where we left off last time. Thank you. This hallway is weird. Like, it's awkwardly silent in this building, but also extremely noisy and disruptive all at the same time. Right. So yeah. So here's our basic point. You know, the two units that we've had in this class so far. The first one was solving things that look like ax equals b. The second was solving optimization problems. And essentially, we've linked the two together by constructing this very special optimization objective function, right? And hopefully, one thing we can all convince ourselves by now in this class is that the minimum value of the objective function on the bottom of the slide is achieved precisely when ax equals b, right? So these are actually equivalent problems, yeah? And so in particular, that inspired us, and the last time, to start by looking at essentially gradient descent, but sort of specializing it just for this objective function, right? So in general, what does gradient descent do? It computes minus the gradient, it adds a little bit of it to your iterate, and it keeps going. But in this case, we have a really nice formula for our gradient, right? It's b minus ax. And so, you know, essentially we're ping-ponging between the formula on the top and the formula on the bottom. And we made one more nice observation, which is that specifically for this objective function, it's quadratic in our unknown variable x, right? And what did that allow us to do? You guys remember? Yeah. Yeah, like we didn't really need line search, right? We could compute alpha in closed form here in a way that makes it as small as possible along that one-dimensional thing, because it's just a parabola, right? And so in particular, that led us to this nice algorithm here. And really, I'd encourage you to, you know, plot your Python or MATLAB or whatever your favorite, Julia, programming language, and type these 3 lines of code in, and you will find that indeed it does converge to the global minimizer and solves the ax equals b, and is a heck of a lot easier to code than Gaussian elimination, which is also not particularly hard to code. But this is a pretty nice trick. But and by the way, this is a reasonable algorithm. Like, it's doing gradient descent. It probably does get a lot of bang for the buck toward the beginning of the iteration, right? And remember that, like, the reason that we like these optimization techniques is we typically don't expect to find the minimizer in closed form. We just get kind of successive approximations that get closer and closer, right? And in particular, there's a proof that's in the textbook. We're not going to do it here because, like, I've already overwhelmed you guys with math symbols on the board. It's a problem in numerical analysis. Like, you know, the other class I teach is differential geometry, and there's pictures, but like here's just a lot of indices. But in any event, one thing you can show is that the convergence rate of this thing basically looks like, you know, 1 over the condition number. So for very ill-conditioned problems, right, this ratio is very close to 1, which is essentially saying that the objective doesn't decrease very much in every step, right? So that led us to ask the question, like, can we do better? Right, in particular, and by the way, one property of this gradient descent procedure, which is absolutely true, let's say that I run it, and I run it for like more than n iterations, right? Which could very easily happen, right? Gradient descent just like successively makes our approximation better and better and better. It never quite gets there, right? So I can imagine for an n by n matrix running it for like 10 iterations. Why would that be dumb? Like, why would that be an unfortunate event? I guess this is a review a little bit from last time. Yeah, that's exactly right. So in particular, if we take a look at our algorithm here, notice that basically the time complexity of this thing, assuming that A is a big dense matrix, is the time complexity here is dominated by just computing the product A times X, right? Like if you guys were writing code to implement these 3 equations here, like doing the matrix vector product is the thing that's going to take all the time. And in particular, it takes like roughly n squared time, right? We can do a little better than n squared for like really ginormous A's, but we're not going to worry about that. So in that case, like if I run this thing for more than n iterations, I've taken cubic time total, and now suddenly I really should have just done Gaussian elimination, and because the good news about Gaussian elimination is that it stops, right? And when it's done, it actually gave me the true solution to my equation, whereas this thing just continues to get closer and closer and closer, but never quite gets there. It's frustrating that way. Okay? So what we're aiming to derive is an algorithm that doesn't have this kind of zigzag property, but rather kind of gives us everything we could possibly want. Like, kind of looks like gradient descent. In fact, we're going to argue that the algorithm we'll finish deriving today outperforms gradient descent in sort of every possible sense of the word, which is cool, by the way, fun fact. And moreover, if I did have to run it all the way for n steps, it stops. Namely, it actually found the minimizer. Like, not that it got close, it actually found the real one, up to floating point precision. Right? This sounds too good to be words. This sounds too good to be true, right? Like this is a lot, but that is the magic of the conjugate gradient algorithm. Okay, so we kind of got midway through deriving it, and then we ran out of time last time. My goal is to finish it today, and then talk about a few variations, namely using preconditioning, which is the sort of standard trick that people do in this space. Conveniently, in my office hours yesterday, Axel was asking about preconditioning, so this is good timing. Okay. Right, so essentially what we're trying to do is to stop after n iterations and still avoid all this repeated work, right? Like we had all this zigzaggy paths that we took to the minimizer. It'd be awfully nice if like somehow we kind of figured out that like really we shouldn't move along the gradient direction. We should move slightly skew to it. That's going to point us right toward the center, right? Okay. So as a quick summary of the math that we proved last time, even if we don't remember the proof, which actually really was just calculation, like there wasn't anything like super exciting. We made the following definition. We said 2 vectors are A conjugate, so V and W are A conjugate if V transpose times A times W is equal to 0. So essentially this is like defining a new dot product, right? And in fact, remember that we can actually kind of formalize that. This chalk is no good. So let's say that I use Cholesky to factor A equals LL transpose, right? Then in particular, V transpose AW is there like a protest going on? Is V transpose L transpose W, I shudder to think, which is really the dot product, right, of L transpose V dot product L transpose W. Yeah, I'm sorry, that's Awkward. I don't know what side the protest is on, so I suppose I can stay neutral here. Right, so we proved the following fact, which is on the screen, which says as follows. Let's say that I have a set of A conjugate vectors, which, by the way, is the same as like the images of the vectors under L are all orthonormal to one another. If I do line search not along the gradient direction, but along these things successfully, so V1, I keep saying successfully when I mean successively, by the way, I'm sorry. So I line search along V1, and then V2, and then V3, which are not gradient directions. Like somebody has just handed me this bag of vectors. Then when I finish line search along Vn, I have found the solution to Ax equals B. Right, that's what we proved last time. We did it by essentially doing a million changes of coordinates. Like that, that was really the extent of the proof. And the way to show it is that it's sort of what's going on here is like if I have a function which is isotropic and centered at the origin, then like essentially what's happening here is like I'm first kind of like optimizing the first coordinate and then the second coordinate like that. Like that's the sort of picture to have in mind. It's just that we've taken this thing and kind of like mapped it to some like weird skew space under that image of L. And that's what's forcing us to use this weird conjugate C property. Okay? All right, Axel. Oh, I just mean like circles, not ellipses, right? Our proof depended on this change of coordinates into a space where we could like use 90-degree angles. Okay. So this corollary here is really nice, right? This is great. This sort of suggests a way that we can get around our problems before, right? If we can take quadratic time to compute each of our VIs, then now we have a cubic time algorithm for solving Ax equals B, right? By doing line search along each of these directions. And so like this is suggesting to us that we're awfully close to all the properties we want. That makes sense? So really, our task here, we need a procedure to find a bunch of A conjugate directions. Do you see it? Like essentially we've reduced our problem. Like we started by saying, okay, like step one was we did gradient descent and that doesn't seem to work that well. Step two was to say we're not going to do descent along the gradient, we're going to do it along a set of directions V. And so long as V satisfies this funny property, then once we do, all of those line searches were done. And that's the nice property we have. You guys are nodding, which is great. I think it's the third time you repeat it that like, then it starts to stick a little. That's great. Okay, and so our task here is to find some design procedure that gives us a bunch of A conjugate directions. That part we haven't done yet. So, that's where we're at so far. And that's where our story ended last time. And then I did some mumbling about Graham Schmidt, but we're going to ignore that. Okay, and the good news is that the microphone didn't catch it anyway, so like, it actually never happened. No, okay. So moreover, we can actually gather some more evidence. Like essentially, we're trying to design conjugate directions here, and we need some evidence for like how to go about doing that. Like, and so we're trying to kind of walk in the footsteps of whoever it was that invented conjugate gradients, Mr. Gradients, and figure out how he or she or they managed to come across this magic formula that we all type into our computer kind of blindly. Because at the end of the day, by the way, this algorithm, like it takes us 2 lectures to derive, but it's like 10 lines of code. It's really easy. I would say it's one of the easiest things that we have to code. So let's gather one more piece of evidence that I think is a good clue as to what to do next. And that's, we can like continue to take our gradient descent algorithm and like just kind of keep reshaping it. Like we have these 3 different inequalities, right? We have these different update formulas. Where are they? I'm going to keep paging around in the slides. I'm sorry. I'm not sorry. We have, no. Computers are hard. We have these update formulas, and we can obviously kind of manipulate them in different ways. And so let's in particular, let's do that. Okay? So, we're going to define a new object, which now that I'm looking at this notation is also equal to one of the things on the screen, but that's okay. We're going to have a slight change in notation. Does anybody know the name of B minus A xk? Like, what is that thing? It's the difference between AX and B? Yeah. Error, yeah, or there's a statistical term for it. The residual, yeah. So let's define RK to be B minus A xk. I think the reason that the book does this, like it starts with D and then it switches to R, is that like D stands for search direction. And R stands for residual, and pretty soon we're going to use the residual, but we're not going to use it as the search direction. Okay? I'm realizing now this is like not the world's best choice of notation, but That's okay. We have this formula for alpha, but that doesn't actually matter quite yet. So here's a fun fact. We're going to write a lot of fun facts today, and then we're going to glue them together in a cute way. Let's say we do the following. What is rk plus 1? Well, clearly, it's equal to b minus axk plus 1. I think we can all agree on that. Yeah? But now we can recursively apply our formulas. Right? So in particular, we have a way to get xk plus 1. Right? This is equal to b minus a, if we kind of squint to the formula at the bottom of the screen, xk plus alpha k plus 1 dk plus 1. Right? Yeah. Make sense? Okay. So in particular, let's kind of reshuffle this thing a little bit. This is b minus axk minus alpha k plus 1 dk plus 1. Yeah? All I did was just reparenthesize this expression, I hope. Chris is squinting at me, which makes me think I made a sign mistake. Okay. Why did I parenthesize it this way? Yeah, this is rk. Okay? So what is this saying? It's saying if we know the residual at step k, we can get the residual at step k plus 1 by subtracting off this quantity here. Cool? I think I'm missing something. Yeah, which is this a. Sorry. You told me I was right, and I wasn't. There was an a that was missing.
I also did remember quiz.
Oh yeah, also we need to write a quiz. Okay. There are definitely some changes that will be made in the next offering of this quiz. It's really a problem. The MIT policies, you cannot adjust anything based on the, so we tell you there's a quiz, we've got to give you one for the rest of the semester. In any event, so there's our expression here. And here's the magic part, which is actually the part I left out. There's an a there, right? It's this a. So if you think about it, what's happening? I take this search direction, and I multiply it by a, and then I add that onto the previous residual, or subtract, right? Now, what search direction did we choose in the gradient descent? Well, remember our search direction is b minus, axk, which is the residual. Now you can see why we chose this notation. Right? We made a decision here, which was when we did descent to do gradient descent specifically, right? And because of that, what is this thing? This is really alpha k plus 1 times a times r k. 1. What's that? Yeah, that's right. So that's why there's a shift by 1 in these expressions here. Okay, that's an RK. Oh, I'm sorry. Thank you, Paul. That's absolutely right. So the next search direction is the previous residual. There we go. I'm already getting all kinds of confused. Now you're all squinting at me because I made an index mistake and you're angry. Whew. So let me see if I can summarize because I did make a mistake here. Good, you're paying attention. I caught you. So here's what we showed. We showed that generically speaking, when we update the residual, this is to just rewrite this formula because I managed to scribble on top of it. This is rk minus alpha k plus 1 a dk plus 1, like that, right? And this is the residual after step k plus 1. dk plus 1 is the search direction in step k plus 1. So the small mistake that I made, that Paul so kindly caught, is the search direction at step k plus 1 is the residual after step k. All right, that's why there's a k plus 1 here and a k there. My apologies. Okay? So in particular, this is what we showed. We showed that for gradient descent, we have rk plus 1 is equal to rk minus alpha k plus 1 a times rk. That makes sense? Okay. All right. Indices suck, and this it just continues to get worse. These iterative methods are really a problem. Okay. So, what can we show about this? Well, one thing we can show, what did? We took the previous residual, and we just multiplied it by a. And so every single time we do that, we're basically, so what do we get? So the first time, we get that our residual is basically just b minus a x 0, right? So we'll just call that r0, right? So basically what we've shown is that rk is in the span of r0 all the way to a to the k r0, right? Something like that. Like essentially every time we compute another residual, we just take the previous one multiplied by a. So we're like in the span of the very first residual and then like different products of a times that guy. Does that make sense? Notice what that means. That means that like when we do searches in gradient descent, if I look at the difference from where I started to where I currently am in that procedure, there's somewhere in this plane, right? Which I can actually pre-compute without doing gradient descent, right? It's just like a bunch of a's multiplied by r0. If this feels like Krylov subspaces, like eigenvalue problems, that's because it is. This is very close. Does everybody understand the claim that we just made and how we showed it? And like, I want you to reflect on what this means. That there's this like the plane that I'm building up by taking the first residual and multiplying it by a more and more times, right? So if I take my first iterate and I stick that plane on top of it, the kth iterate is somewhere in that plane. That's what we've shown. We haven't shown that it is the optimal point in that plane. We've just shown that it's in it. In fact, it's not optimal. Okay. And guess what? Conjugate gradients will be. Oh no, I gave it away. Okay. Okay, so there's our little proof. So basically, yeah, there it is. When we're performing gradient descent on f, the span of all the residuals equal to the span of these guys. And in particular, what that means is that if I remember that I got xk by like adding different multiples of these r's, that like basically xk is somewhere in the span of these guys plus x0. Cool? I repeat everything 3 times because by the time it comes out the 3rd time, it's correct. Okay. And this does look like a Krylov space. That's what it is. Because like this looks an awful lot like how we computed eigenvectors, right? And that actually, you know, like when you look at the proof of conditioning for gradient descent and conjugate gradient, right? They're basically using this fact, and that's why the condition number ends up popping up. Because remember, condition numbers are related to eigenvalues. Yeah, so all these things fit together. Okay. But here's an issue with gradient descent. This is why gradient descent sucks. So what have we shown? If we look in the slide, essentially a different way to write what we've just proven, that I've said out loud like 8 times now, is the following, that if I take xk and I subtract off x0, it's somewhere in the span of r0 to a to the k minus 1 r0. Sorry, there should be a minus 1 here. Right, that's like essentially the takeaway from our proof here. But look at the screen. So we've shown that it's in the span. We have not shown that it minimizes f in the span. It's just a point, right? So if this did hold, notice like if I could somehow prove the property that it is always optimal in the span, then by the time I'm done, right, by the time I've taken n steps, the span of this thing is Rn, because I have n vectors, then my algorithm would converge to the minimizer, right? That's going to be yet another outline for conjugate gradient. Does that make sense? And if you think about it, that little theorem that we proved about A conjugate directions shows you precisely this, that if I have a set of A conjugate directions, it is optimal in the span of those guys. So this is just even more evidence for the fact that it would be really nice if we had a set of conjugate directions. That is the takeaway you should get from our math so far. Conjugate directions are nice when it comes to gradient descent. Okay? So here's going to be our outline for our algorithm. Somehow, generate a VK. We don't know how yet. And then the rest of these steps are exactly the same as what they were before. Does that make sense? And our goal is to choose a VK that is A conjugate to all the VKs that we've seen so far before that. Questions? There's still like a bunch of question marks, like how to do that, but hopefully you guys get the strategy. Like the reason that I'm trying to present it this way is so you can maybe see how somebody got got to this point to begin with. Because the algorithm itself, like usually people just kind of like put it on a page and say, ta-da, conjugate gradients, let's analyze. I think that's like the worst possible way to think about this. Okay, so this is all it is. It's just like steps 2, 3, and 4 are the same as gradient descent. The only thing we've done is replace our search directions with V's, and we've shown that so long as the V's are a conjugate, then like we have this nice property that it converges completely, right? Moreover, we know one additional thing, which is that if we looked at this set of search directions in gradient descent, they sit inside of this span, right? So a reasonable strategy might be, can I make successive directions v that are in the span of these guys, right? Because in that case, like I know I outperform gradient descent, right? Because I always have this nice property that I'm the minimizer in the span. Yes, Axel. Sure. Here's going to be the basic thing that we're going to try and do. We're going to always try and show that I'm going to get my multiples of k off. So let me think for a second. Yeah, here's what we want. For all k, it'd be kind of nice to have vk to be in the span of r0 to a to the k minus 1 r0. Now I claim that this is a nice property to have. We haven't shown how to achieve that yet because we also want, and like we can do that this much by gradient descent, but we're going to add a second thing, which is that we want v1 to vk to be a conjugate. Okay? And if we have these two things, then we can essentially prove two conclusions from that based on the math that we've written down so far. The first one is finds x star after n steps, right? Because that follows from A conjugate C. That was what we proved in our previous lecture. And then the second thing is that, remember we have this objective functional f, right? Which is the thing we're trying to optimize. What we can show then is that fk, like I actually evaluate my objective at the current iterate, is always less than or equal to fk for gradient descent. And this comes from the fact that essentially conjugate gradients kind of always remains optimal in the space that it's seen so far, whereas gradient descent is not, right? So all of these beautiful magic properties are enabled so long as these two things are true, okay? So that's where we're at so far. We don't know how to do it, but these are the properties we want. Yeah?
Does the order matter?
No, not so far. It turns out it will for other reasons, like for conditioning, like if for instance, if I ran conjugate gradients and I remembered all my directions and then I ran it backward, the convergence rate would be really bad. But you're right. The order of the VKs doesn't matter for all the properties are written here, except for one, by the way. Notice that this thing, if it holds for all k, right? Then think about what kind of has to happen here. So the first VK had better be parallel to R naught. The second VK is in some two-dimensional space, right? R naught and A times R naught. But I already had a previous VK that I committed to. So the second one has kind of got to be A orthogonal to the first one. The third one's got to be A orthogonal to the previous two. This is actually kind of deterministic definition. There's only one vector I can use at each step up to scale. Yeah. And that's going to actually be important in a minute. Yeah? This part does, yeah. Right? What was that? Yeah, that's right. So it never does worse than gradient descent. We haven't shown that it does better. In the book, there's actually some discussion that talks about the convergence rate is actually faster. But we haven't shown that, yeah. Okay, so yeah, so this is a nice algorithm. Because essentially, if we have these properties, that was on the slide the whole time, which I honestly forgot about, which is why I wrote them here. Then it converges in n steps, and it's always better than gradient descent. Yeah. It turns out, like relative to Harry's question, like the way that I've written it here, this is a boring property. Like I kind of might as well use gradient descent. But like it turns out it's always better by a nice factor. Like they're actually so gradient descent looks like 1 minus 1 over the condition number, and conjugate gradient looks like 1 minus 1 over the square root of the condition number. Yeah. Okay. So the question is, how do we get conjugate directions? Hopefully by now I've convinced you guys that if only we had these things, our life would be pretty damn good. Yeah? So, do we have any ideas? How can we do it? We have a set of k vectors, r0 to ak minus 1 times r0. And we want to make them basically orthonormal with respect to a. We have an algorithm for that. Graham-Schmidt, right? So that suggests to us this algorithm. This is what a lot of textbooks, which is like a total straw man. You should never code this. If you do, I will hunt you down. You're like, don't write this on your computer. This is just a mathematical object. This is called the method of conjugate directions. Okay? And here's what it's going to do. This is literally Gram-Schmidt. Do you see that? So it takes ak minus 1 r0, so like the very last vector in this set, and it says, I need to make sure that it is not parallel to any of the previous vectors I've already computed, so it just projects each of them out, right? Do you see that like this is Gram-Schmidt, where every time I used to have a dot product, now I just have an A inner product? Everybody with me so far? Nods? Some kind of confirmation? I get it. I'm excited. Conjugate gradients is super cool. Okay. And by the way, notice I constructed the previous VIs to already be orthonormal, which is why I don't have any cross terms here. I didn't need like a QR. Okay. So why is this algorithm no good? I think there's sort of two reasons. Come on, people. Yeah, I know you know a little bit. So first of all, let's say that my conjugate gradient algorithm takes like 1,000 steps. So like k could get really big, right? Which is typical because these are like these are algorithms. By the way, like this looks like innocent math. Like A is a cute letter, but like these are like 1,000, like a million by million matrices. These are big objects. Okay. So what do you think is going to be the difference between a to the 1 million minus 1 times r naught and a to the 1 million times r naught? Like think back to our eigenvector lecture. They're going to be very similar vectors, right? As k gets big, all of these objects, right, all the a to the k minus 1 r naughts, they're always going to look almost identical to each other, right? Because they're all going to be parallel to their first eigenvector of a, right? This is just the eigenvector iteration. Do you see that? So this projection step is going to get worse and worse conditioned, right? Like the more we go, the tinier and tinier that projection is going to be, and the bigger and bigger this product is. Yeah? So that's no good, right? So to put it differently, so a to the k minus 1 times r naught looks like the largest eigenvector of a. The projection is poorly conditioned. And moreover, there's a second more subtle issue. I have to store all the VIs. Do you see that? In order to evaluate this formula, I need to have memory that remembers every single one of my past iterations of gradient descent. And that's no good, right? Like I don't want that. And in fact, like how much time does this thing take to evaluate? Quite a bit, right? I have to iterate over all the past guys. I got to remember these things. The big dense metrics, no good. Okay, but hopefully we'll agree that like if I use this VK update, then certainly these properties are true. It's just a very slow algorithm and not very numerically smart. Cool? Cool. So we're going to address these two problems one by one. We're going to address the first guy first and the second guy second. And so the first thing that we're going to do is we're going to use a different vector than a to the k minus 1 r naught, and one that's easier to compute. And then the next thing we're going to do is we're going to notice that we actually didn't need to store all the VKs. I would say the first one is like a totally reasonable engineering next step, and the second one is like some weird magical fact about the universe that God handed down, and it's just like a magical coincidence about this algorithm. Okay? But I think there's kind of a funny thing, which is if you had actually coded this algorithm and then did the one next step we're about to do, and then you're just going to like look at the iterates, you'd notice a pattern, and then you'd conjecture and actually prove it. But it's not obvious why this should happen. So first of all, we don't really like computing these vectors, right? These are weird big vectors. They look a lot like eigenvectors of A, the same eigenvector of A over and over again. So instead, here's the point. What did we do? We took a vector in this span, and then we just kind of projected out the span of the first k minus 1 of them. Do you see that? But like really, so long as we took some vector in this span that wasn't in the span of the first k minus 1 and projected it out, you get the same thing up to scale, right? Like it doesn't matter which. So in other words, in this expression here, this vector a to the k minus 1 r naught is not special. I could use just an arbitrary thing in that span. Okay. So here's going to be our trick. Remember, we have this magical formula. We have this residual update. Yeah? What does a residual update do? It takes the previous residual and it subtracts off some multiple a times vk. Now let's think inductively for a minute. So vk is in the span of all of these terms except for the last one. And so is the residual, by the way. Yeah? And now I multiply that by a, what happens? Well, it's certainly in the span of all of these guys, plus one more thing, which is a times that. Yeah? And so this object is actually in the space that we want. So here's what we can do. Rather than projecting out this weird object here, we're going to instead just project out the last residual. And that's actually good enough. Sneaky, huh? Here's a different way to think about it. So what is the residual? It's sort of the vector from like ax to b as x gets better and better. So like necessarily it's kind of pointing out of the span of the directions that you've seen so far, right? Because you're optimal in the span of the directions you've seen so far. So like clearly it has an interesting component to it, right? Which is kind of all you need. Okay. So now our method of conjugate directions looks a little bit better. Essentially all we did here is every time we had a to the k minus 1 times r naught, we're just sticking in rk minus 1 instead, and we convinced ourselves that that was an okay thing to do. Okay, any questions so far? So this absolves us from our first problem, right? We no longer have a bunch of like ill-conditioned matrix multiplies, but we still have to remember all the v's, so that's not so good. Okay, any questions? So now, we get to do the dramatic the dramatic reveal of the conjugate gradient algorithm. And this is just so cool. This is dramatic and amazing, and whoever, like you could have coded this algorithm so far, it would be like ugly and quartic and hard to store. But then I'm sure what happened is somebody coded this thing, and then they actually looked at these dot products. They computed them all. You maybe plot them. You know, you have Python or Fortran or whatever it was back in the day. And there's a beautiful observation you can make. Anybody have any hypotheses? Bunch of them are 0. Yeah, in particular, all but 2 of them. That actually this dot product, r dot v, is just equal to 0. And again, let's go back to our algorithm for a second here. So again, remember, this is our projection formula. Essentially what it's saying is that the numerator in this little fraction here is almost always just 0. This is surprising. This is not intuitive. It is not clear why that should be the case. The proof of it is a little technical, but it is a thing that you could have reasonably gotten like empirically, right? You could have coded this crappy algorithm and just noticed you got a bunch of zeros when you did it, which is my best guess for the history of this technique. Okay. So, first of all, if we skip the proof of the proposition for a second, notice that like what that means is in our method of conjugate directions, that sum is no longer necessary. It's just one term. You just have to project off the very last guy. Isn't that cool? And moreover, I no longer need the memory, right? Because my memory only needs v at the previous iteration. It doesn't need anything more than that. This is one of these universes where like everything you want to be true is true. I wish this were the case in more corners of computer science, but like this is the one case where it like really is. Okay? So now the question is, do we prove it or do I get lazy until you read the book? Yeah, well, you think I've gotten the indices wrong so far. You just wait. It's all about what's about to happen. Okay. And my warning for you is this is like a technical proof. Like, and really, my best guess is that somebody just like literally coded this thing up and noticed it and then spent a bunch of time trying to prove it. Like, I don't know what geometric picture I would draw to convince myself that this picture were accurate. There might be one. I challenge you guys. Maybe there's some natural property here. Okay. So what strategy do we typically use for proving these kinds of facts? Induction, right? That seems like a reasonable thing. We want to make some fact about, probably want to do induction on K, right? Okay. The first thing we have to do is our base case, which is K equals 1. And I claim this is good because there are no terms less than K equals 1. So this is true just because it's an empty fact. Okay? So the real hard part of the inductive proof is the inductive step, which I think is almost always true in life. Except for one, there's like this interesting little internet puzzle that goes around with this like inductive proof that like 1 is equal to 2 or something like that, and it's actually the base case that's a little bit wrong. But I digress. Okay, so now assume that K is bigger than 1, and that the result holds for all k prime less than k. This is like a sentence that when you guys took your first proof class, you probably wrote down like 600 times. And now what we need to show that the result also holds for k. Right? That's our usual task here. Okay. So we're actually going to do this in 2 different cases, but the first thing we're going to do is write a convenient formula, which is as following, which is we're going to take rk, the residual at step k, and inner product with v at step L with respect to A. Hopefully now we're starting to remember what all these objects are. So V is the search direction, R is the residual, A is the matrix of the dot product. Okay? So we don't really know much about the universe, but the one thing that we're going to keep reusing, which I've conveniently erased, oh, I haven't. For once, I didn't, is this residual update formula that we already had on the board. Okay? So in particular, let's plug that in here. We're going to get that this is equal to rk minus 1 inner product with VL minus alpha k a vk inner product VL. Right? That's our residual update formula. Okay. Hopefully I've done that right. Yes. Okay. So now here's a kind of useful fact. I claim that this thing is equal to VK inner product with A times VL. Okay. Why is that? Like so remember what this inner product really is? It's like VK transpose A transpose, right? That's this A. Then there's this A. Then there's VL. Like that. So now if I kind of parenthesize it like that, remember that A is symmetric, so I can get rid of this transpose, then I get this expression here. Cool? All right, so everybody agrees that this is an okay formula? Okay. That's good, because essentially what we're going to do is claim that both of these terms equal 0. Okay? So we're going to do this in 2 cases. In case 1, we're going to have really small l. Namely, L is not just less than k, L is less than k minus 1. Okay? So like this is like a way earlier vector in my basis, right? That's what I'm worried about here. Okay. So let's number these terms, by the way. Let's call this thing 1 and this thing 2. Okay? Then maybe we'll make our 2 cases here, A and B. Okay. So what is 1? It is rk minus 1, so it's the previous r dot producted with an even more previous v, right? So I claim that 1 is equal to 0 just by induction, right? Because that's actually our inductive hypothesis. Does that make sense? Remember, our inductive hypothesis is precisely that r dot v is equal to 0 for all the previous case. Everybody with me so far? Okay, what about 2? Well, notice, so we have this A times VL here, right? So AVL, this thing is in the span of V1 VL plus 1. Why is that? Well, it's certainly in the span from V1 to VL. Yeah? But, or VL is, and now I've multiplied it by A. But remember our residual update formula? It just keeps saying that like basically every time I do a step of this algorithm, I incur a product with A. So as long as I add one more index here, we're still good. Okay? But because of that, what do we know? So this guy is in the span of the first however many terms. The k is bigger than L plus 1. Yeah? So now this is equal to, the second term is equal to 0 by A conjugate C. Right? So the basic point here is that like the v's are all kind of orthonormal to each other, or orthogonal at least. Right? AVL is in this span here. That's right? Yep. And since it's in this span here, and then we've kind of got it, like if I continue the sequence, I'll get vk somewhere, right? Since this whole thing is an orthogonal sequence, in particular, this thing, dot product with anything here, is orthogonal. Okay, and that's why the second term is equal to 0. Okay, so that's case 1 where L is like very small. So really, we only have to worry about L is equal to k minus 1. You can see this proofs are just technical and ugly. It's okay, like as soon as we finish proving this, if you forget, I'm not going to be offended. It's okay. Yes, Axel? Oh yeah, we're already like in pretty good shape. Now we're just shaving off one more term in our sum. Yeah, but you know what's better than storing 2 vectors? Storing 1. Or 0, but sadly we do need to store at least 1. Yeah, but you're absolutely right. Like if like for some reason the inventor of conjugate gradient got so close and was able to prove this fact, but not, you know, more, like the algorithm would still be kind of fine. He'd just be storing a bunch of zeros. Okay, but we're not that person. We're students in 6S955, and we can do better than that. We can shave off that last set of values. And let's do that by causing your instructor to have a lot of discomfort with indices. Okay. So, in particular, okay, so now we've got case, I guess, B, which is going to be L is equal to k minus 1. Okay. All right. So, remember our residual update formula. Which, oops, I just erased. So let's copy it. So we have rk plus 1 is equal to rk minus alpha k plus 1 a v k plus 1. Right, that's our formula. I keep erasing it and then needing it and then having to write it again. Okay, so now we're going to prove yet another useful recurrence. There's many of them in this domain. And that is the following. I'm going to take the previous residual, and I'm going to subtract off the residual before that. So here's what this looks like. R k minus 2 minus r k minus 1. This is the expression we're after. You'll see why in a minute. Okay? So what is this thing? Well, this is rk minus 2. And now let's apply our residual update formula. So this is going to be, you have to basically subtract 2 from every index here. Right? So this will be rk minus 2 minus alpha k minus 1 a v k minus 1. Everybody agree? I think I've managed to get it right. Okay. So a nice thing just happened. Do you see that? In particular, these two guys cancel, right? So this thing is nothing more than alpha k minus 1 a v k minus 1. Which you kind of already knew. I mean, that's like in some sense exactly what this residual update is saying, right? It's just saying that every time I change my residual, this is the amount that I add. So it's like totally reasonable. This is what I got. Okay. So now we're going to pre-multiply both sides of this thing by, in fact, I should just write this down because this is annoying. By, where are we in my notes? RK transpose. Okay. Oh, by the way, we can rearrange this ever so slightly. This doesn't really matter, but just for fun, this is obviously the same as a v k minus 1 is equal to this whole stuff divided by alpha, right? R k minus 2 minus r minus 1 divided by alpha k minus 1. This alpha is really pesky. It like doesn't affect our proofs at all. It's just like an annoying thing we have to carry around everywhere. So yeah. Okay. So if we take this expression, we pre-multiply it by RK transpose. What are we going to get? Well, on the left-hand side, we get RK transpose times A times VK minus 1. But that's exactly the definition of the inner product, right? So I can write it as follows. This is RK VK minus 1 inner product A, right? That's exactly the left-hand side. And the right-hand side is whatever it is. So it's 1 over alpha k minus 1 RK transpose RK minus 2 minus RK minus 1. Okay, everybody with me so far? Great. Notice, let's see. What have we done? What is term 1 in our expression all the way up here? Well, it's precisely this, right? Because remember, we've chosen L to be equal to K minus 1. Yeah. So we're just basically doing a lot of work to show that something's equal to 0, right? Like that's all we're doing here. Okay. So RK, this difference, if you think about it, by our residual update, right, our favorite formula, the one that we keep using, right? This thing is in the following span. It's in the span of R naught, A R naught, all the way to A K minus, it's a minus 1 R naught, right? This is by the residual update formula. Because again, every time we do a step of our algorithm, we incur a factor of A, right? That's the, you know, when you're brushing your teeth tomorrow morning, that's what you should be saying. Okay. So this is where our proof gets a little bit funny. So we know the following kind of fact, which we actually proved last time, that if we apply a conjugacy like that, right, xk is optimal in this span. So in other words, like if I took xk minus x naught, right? So like I looked at that difference. For any other difference in this entire plane, xk has got to be the best possible thing I can do. Right? That was the point of our proof, right? Like that we never have to look back in our set of directions. So in particular, rk is actually, by definition, it's minus the gradient of f at xk, right? At the end of the day, we've probably forgotten because we're doing all this notation, but we're doing some version of gradient descent, and gradient of our objective functional is rk, right? Okay. So what do we know? We know, if we're optimal in the span, that in particular, when we want to walk downhill, it's got to be perpendicular to the following span. R naught. Do you guys see why this fact is? That like I have an objective that I'm saying like in the plane that's spanned by all these vectors, I have optimized my function. I can't get a lower value. So necessarily, when I take the gradient of that function, I won't end up moving around in this plane. I'll move 90 degrees to this plane. That's what this is saying, right? What does that mean? That means if I take rk and I take its dot product with any vector in this span, I'm going to get 0. Well, wait a second. Okay. Take a look. I've got rk and I've got its dot product with two vectors in that plane. So in particular, this thing's equal to 0. Check mark. Okay, so that shows us that our first term is still equal to 0. The second one, the proof is still holds, and we're good. Cool? Sneaky, huh? It's kind of funny because like we do all this linear algebra, and then the very last step we use a tiny amount of calculus. And the basic point here is that the one beautiful property that we have for conjugate gradient is that at every step of the way, if I look at the plane that's spanned by all the iterates I've seen so far, I'm globally optimal. I can't do better. Meaning that if I take the gradient of f, it always points 90 degrees to that plane. So even if I don't choose to step along that gradient, that property is still true. And that's what we use to prove this fact. So, ta-da! We now have a much nicer update for V. We thought we were doing Gram-Schmidt. We are doing Gram-Schmidt, but actually this is the one case where Gram-Schmidt is kind of okay because all the terms are 0. Yeah. Incidentally, you might ask, like Gram-Schmidt, I mean, we spent all this time in this class talking about how Gram-Schmidt is numerically a bad idea. We actually haven't gotten rid of that problem here, and indeed, conjugate gradients can stall for weird numerical reasons if we run it long enough. We'll come back to that in a minute. Okay, so this leads us. Like, I'm trying to like get you people excited, and you're all just looking sad and staring at your computers. To an algorithm, which is wildly elegant for solving ax equals b. This is so cool. It is so clean. Do you see that? So basically, the only thing I did, steps 2, 3, and 4 are exactly the same as the otherwise spin, right? This is just line search. And all I did was use this weird magical update for VK, which is basically just Graham-Schmidt on this set of vectors. Cool? Not at all obvious when you set out to write down this algorithm that it's going to come out this cleanly. Okay? And this gradient descent, or rather this conjugate gradient algorithm, has a lot of different properties. First of all, xk is always optimal in the subspace that's spanned by the first k directions, right? That's what we showed yesterday. Moreover, f xk is upper bounded by f at the kth iterative gradient descent, which, by the way, is sort of just a reflection of the first bullet point. And in n steps, because of the first bullet point, once again, we know that after, in that case, I'm optimal in all of our n. So necessarily, I'm just done, right? Which is good, because it means we never do worse than Gaussian elimination. Isn't that cool? This is a really cool algorithm. So I went back to the diagrams that we had for gradient descent, and I updated them for conjugate gradient. The problem is that the screen is two-dimensional. So here's what they look like. They're just a bunch of pairs of two line segments. Because we just showed, right? We just spent all of this time showing that necessarily conjugate gradients converges in 2 steps in the plane. And indeed, if you just write out this code, this is precisely what happens. Isn't that cool? So now, right, so the form of conjugate gradients that we've done so far is sort of a byproduct of our proof. Right, I mean, I kind of like this form because steps 2, 3, and 4 are really obviously the very first equation. So even if you don't believe 1, 2, 3, and 4 are pretty clean. And then 1, at the very least, you kind of see that it's like some combination of RK and the previous V, so you know that it's in the span. Like it's somehow, the only thing that you don't know is that they're conjugate, right? And so actually, a much more direct proof of this technique, which I think would be totally obtuse, would be to write this four formulas down and then just show that the VKs are a conjugate. Right? You could easily do that by induction. But I think this is a nice way to understand what's going on. Yeah? That's our residual. That is our line search formula. Yeah. If you look back, that was actually exactly what it was. One of them is V and the other ones are, I believe, unless there's a typo. We can go back and look. Let's see if I can do it really quick. No, I'm not going to bother looking, but you can look in the book. I could have. Oh, but the reason for that. Remember how we switched from the D to this notation with the R's and the V's? We have now divorced the D, which is the residual, from the D, which is the search direction. So if you go back to that formula, really only one of them was the residual. Yeah, sorry. That's what's going on. Good question. Any other? So this is a clean, again, at the end of the day, even if you didn't understand a single word of that proof, notice that this is a really easy algorithm to code up, right? You just have to do it really carefully. I can tell you from extensive experience coding this, I spent like my entire time at Pixar just like coding these 4 lines of code over and over again. If you get any one character wrong in this formula, the whole thing diverges and dies. So you have to be very careful typing these in. When I was writing the book, because I remembered my old pain coding this thing up, I was so careful to try and make sure all those little boxes, the algorithms were correct, because it would just be evil to get one of those wrong. The reality is when you see conjugate gradients presented, there's like a lot of different equivalent formulations where like, I mean, we have all these recurrences, right? Like the same way that we made the residual update formula, like we could have plugged that in here, we could have done, like there's all kinds of simplifications you can make. So just for completeness, here's the sort of, oops, for some reason the laptop like updates my screen a lot faster than it updates the projector. This is the form you usually see it, and this is completely unimportant, other than they basically just parenthesize the formulas differently. And this is precisely the same sequence of x's. All they've done is just done some substitutions. So I don't think it's worth proving this in class, but like essentially you can just make some convenient definitions. The reason to do this is if you look at this algorithm, notice that there's only 1 multiplied by a here, whereas in the form that we wrote down, there were a few a's kind of floating around in the expression, so that's why people usually write it this way. Does that make sense? Yeah?
It might just be because it's a iterative algorithm or
Mm-hmm.
something, but this feels like
Could be. Leslie Kelbling tells me that like all methods are secretly Kalman filtered. I don't know enough about Kalman filtering to say, but I mean, I do think this is one of these like very classical famous algorithms that's been analyzed to death. The other thing that you can do is take an interesting limit where the line search, like the dimensionality gets big and the alpha goes small in just the right way. And there's this entire series of research papers in actually machine learning a couple of years ago from Boyd's group that model, like you can think of gradient descent as some kind of ordinary differential equation, right? Like in some sense, it's like dx dt is equal to the gradient. You can try to figure out what is the ODE that is modeled by conjugate gradients, and such a thing exists, but it's hard to see from this formula. So this is just like one of these things that it's this extremely famous algorithm, and everybody has analyzed it to death. Like there are all kinds of different ways to understand.
You still view it as an ODE. I feel like this is a
Very discrete object. Yeah, you might kind of ask, like, if you want like some kind of physical system that flows downhill, like, what is this thing doing? It's not walking to the gradient anymore. It's like kind of walking in this weird direction. Yeah, I don't know. I don't know the right way to think about it. In any event, yeah. So that is the theory of conjugate gradients. Now I have to talk about some practical stuff. First of all, does it make sense to check, like when should I terminate this algorithm? And so one option would be to just run it for n steps and stop. Should I do that? I mean, I think there's sort of two reasons not to. I mean, on the one hand, the residual here, like it should go to 0, but of course all these things I'm implementing in floating point arithmetic, so they're all slightly wrong, right? All the theory that we wrote on the board was very much dependent on never making an arithmetic mistake, right? And computers don't work that way. And so a very typical thing, actually it turns out numerically, what tends to get messed up is this residual update formula here, right? Because this is where products with A are being incorporated. You see that? Like nowhere in the rest of this expression, well I guess actually with the exception of this guy down here. But notice this is the same A times BK that shows up twice. So essentially what can happen is numerically the residual starts to be a bad estimate of the residual. And so in practice what people do is every once in a while they won't use this one. They'll do like the true formula for the residual. Like they'll just plug in some stuff to make sure you kind of push this back to the ground truth. Yeah. So if you look at the pseudocode in the textbook, you'll see that it suggests like one every 100 iterations or so, like do the slightly more expensive update. Yeah. The other thing is that like we have shown that this thing outperforms gradient descent, so it might be perfectly fine to just stop early, right? To say like I walked downhill enough and I have a good approximate solution to my linear problem, and so I'm just going to satisfy myself and stop, right? I don't need to actually run for n steps. I think in practice people run for much fewer than that. To go to Carrie's question from before, the question might be then like, well, how many steps do I need to kind of think that I'm like within some radius of having solved my problem, right? And indeed, there is a convergence result. It is very difficult to prove. By very difficult, I mean like more calculation and like don't make me sweat, like enough already. Which essentially shows that like you have a very similar formula to what we had before, but now it involves the square root of the condition number instead of the condition number, which is a good thing. Remember that like big condition number equals bad matrix, and square root of big number is much less than big number. That's the way to remember this stuff. So it's not just that it outperforms gradient descent, it's that it outperforms it by like a nice factor. Okay. That's conjugate gradient algorithms. We've got 15 minutes left, which is exactly what we need, because conjugate gradients method is also mildly useless without a lot of accoutrement that people typically build on top of it. In particular, remember our initial example? Like we had this banded matrix that was like, where did my, we had a matrix that looked something like this. And this was for solving some version, some very small version of Laplace equation. We wanted to invert a matrix that looked like, you know, I think it was like 2 minus 1, minus 1, 1, minus 1, minus 1, 1, minus 1. Right, these like 3 bands of numbers, something like that, right? And the cool thing about matrices like this is that they're 0 almost everywhere. Now, here's a fun fact. Anybody know the inverse of this thing off the top of their head? If you're really good at Fourier analysis, you might be able to. But even if you're not, here's all that matters for this class. It's a giant dense matrix. There's not a single entry in that matrix that is non-zero. But let's think about why that might be problematic. So we have this positive definite matrix. By the way, it might be negative definite the way I've written it. I forget what sign you need. And now I have this algorithm. And I've argued to you, in fact, we've proven, actually pretty carefully, that this thing eventually solves AX equals B. Right? In other words, it's computing A inverse times B. Yeah? So, at the end of the day, let's say that I multiply this by some vector. I'm going to do this kind of schematically here. And let's take a look at entry 1 here. So what is entry 1? Well, it's the product of the first row and the first column. Yeah? So necessarily, notice that like information from every single element of this vector is getting used to produce this one element here. Right? Because again, matrix multiply like that. Now let's look at steps with the gradient, conjugate gradient algorithm. In every step, I don't multiply by A inverse, I multiply by A. Right? So where does information get communicated? Well, in one step of this algorithm, information gets communicated from this guy to his two neighbors. And that's it. Do you see that? Because this is a banded matrix. So before these two entries even communicate with one another, I need at least n iterations, or maybe n minus 1, of conjugate gradient method. That doesn't even mean that I've solved the problem. I guess in this case it does. But like all this is to say that like for sparse problems, it takes a long time to just have communication happen in an algorithm like this. Like every time I multiply, you know, I've got this sort of, by the way, this is a line graph, right? Like if you think of the non-zero values in this matrix. So you can think of this whole algorithm very abstractly as I take all of the unknowns in my data, and in every step of this algorithm, I'm just like communicating information to my neighbors, right? That's what that matrix vector product is doing. And so it takes a very long time for them to reach consensus. Does that make sense? And this is generically true. I mean, like even if this weren't banded, like maybe this matrix now has some non-zeros that point elsewhere, like it sort of takes a lot of time for information to diffuse around. So very typically, running conjugate gradients on the very first matrix that's presented to you is a bad idea. The convergence rate will be very slow. And so in practice, people have all kinds of magical tricks for making it better. That's what we're going to talk about next. And here's going to be the trick. Okay. Sorry, all my notes look the same. So here's a fun fact. We have a lot of them in this class. Let's say I want to solve AX equals B. Okay? This is our goal in life. Okay? I claim that I can solve an equivalent problem. Let's say that P is an invertible matrix. Okay? Then I can solve the following. PAX equals, PB. Right? Obviously, these are equivalent problems as long as P is invertible. Are they equivalent from the perspective of conjugate gradient algorithm? No. In particular, let's say I make a really smart choice of P. Some might call it a smart choice, some might call it a smart ass choice of P. In particular, the best of all universes, I take P to be A inverse. Now, conjugate, what is the condition number of P times A? 1. What is the condition number of A? I don't know, but it's probably not 1. You see that? So the convergence rate of conjugate gradients absolutely depends on stupid things like pre-multiplying my system by some other matrix. Of course, there's a problem, which is if I knew A inverse, I wouldn't need conjugate gradient. Yeah? So like this strategy is not so smart so far. But the basic observation here is that the conditioning of A and the conditioning of P times A are not the same, but I can still solve PAX equals PB. And so what I can do is design P's whose inverse I do know and use them to kind of try to make the condition number a little bit better. Does that make sense? That's going to be our sneaky trick. And by the way, this is a totally reasonable thing. So to give you an example, let's say that I have a matrix which is almost diagonal, right? So like it has a bunch of like entries. That was supposed to be a 2, and it ended up being like a cute 4, like that. And then it's got noise here. So it's like a bunch of big numbers down the diagonal, and then numbers that are not quite 0. What is the inverse of this thing approximately? Well, approximately, it's 1 over d1 to 1 over dn just zeros, right? Because if the noise wasn't there, that's what this inverse would be. And this object I could use for P, and it probably would make my condition number a heck of a lot better. This is actually a very simple strategy. People call it diagonal preconditioning, and it is absolutely a reasonable trick. It's to just take 1 over the diagonal of your matrix. It's not the best trick, but it is a trick. Okay. Does everybody understand our trick so far? So like basically, we're going to go into conjugate gradient. Every time we see a P, or an A rather, we're going to replace it with PA. Yeah? What's the problem with that strategy? Well, we assumed that A is symmetric and positive definite. Can we say the same thing about P times A? No. It's here. So I can't just like choose an arbitrary P. I need to be more careful than that. PA is not necessarily symmetric or positive definite. By the way, choosing a P so that it is symmetric and positive definite is a dark path. You don't want to do that. I'll let you think for linear algebra reasons why. So what we're going to do instead is we're going to choose a P where this product is not symmetric positive definite. It is positive, well, as we go. Yeah, it's not. But an equivalent problem is. And then we're going to kind of unroll what we did. Here's going to be our trick. This is so much fun. Okay. So we are going to choose a P that's positive definite. That makes sense, because all conjugate gradients is for positive definite matrices anyway. So like preconditioning with a -1 would be kind of a dumb idea, right? So we're going to assume that P is symmetric and positive definite. Cool? So in particular, if you're symmetric and positive definite, so is your inverse, rather. So your inverse has a Cholesky decomposition. I can write it this way. And again, this is going to be just like our proof yesterday. Like we're going to write a Cholesky decomposition, prove stuff about it, and then never actually use it. This is just a theoretical object. So first of all, we can prove a fun fact here, which is the following. These things have the same eigenvalues. Okay? So here's how we can do it. Suppose that I have E minus times A times E to the minus transpose X. And we're going to say that this is equal to lambda x, like that. Okay? Well, what was I doing? Oh, yeah. So now, if I pre-multiply by e to the negative transpose, right? So I get e to the minus transpose e to the minus 1, a e to the minus t, x equals lambda e to the minus t x, like that. Okay, what is this product here? Well, remember, P inverse is equal to whatever it is, E transpose. So P inverse, namely P, is going to be E to the inverse transpose E to the minus 1, like that, right? So this thing is P. This is A. Let's give this thing a name. Let's call it Y. Then notice P, A, Y equal to lambda y. So in particular, for every eigenvector x of this guy, I have an equivalent eigenvector of P times A with the same eigenvalue. Does that make sense? So in particular, the condition number of PA and the condition number of E inverse A e to the minus transpose are actually related to one another. Do we have time to prove that? Sure, we can do it really quick. So, oh no, that's fine. In particular, like so far we've shown that they have the same eigenvalues, but we've not shown that they have the same condition numbers. Not quite the same thing. Remember, condition numbers involve singular values. But notice that singular, let's look at the max singular value of P times A. Okay? And remember what that is. That's equal to max of some vector x is equal to 1 of the norm of PA x. Right? That was our definition of singular value from a long time ago, in case you forgot. Okay? So in particular, if I plug in any x, I get something that is upper bounded by the max, right? So if I take any eigenvector, then I get this is greater than or equal to PA x naught. PA, which is of course just lambda x naught. Right, so what did we show? We showed that for any eigenvalue of PA, it is upper bounded by sigma max. And by basically a symmetric argument, you can show that sigma min is less than or equal to any eigenvector of your matrix. Okay? Which is exactly what you need, because the condition number of PA is equal to sigma max of PA divided by sigma min. So what did we show? We showed that lambda max of this matrix, let's see. So lambda max is smaller, right? Lambda min is bigger. So in particular, this is greater than or equal to lambda max over lambda min. Yeah. And this is actually exactly cond of the other guy. And the reason for that is that this matrix is symmetric positive definite. So this guy's eigenvalues are its singular values. That is not true for PA because it's not symmetric. So what we showed is that like it upper bounds, which is great because if P is a good conditioner, preconditioner for A, then an even better way to precondition A is to conjugate it with its Cholesky factorization. Does that make sense? That's what we just showed. So here's the thing. This thing is symmetric and positive definite. Do you see that? So this suggests a strategy. I can solve a pair of systems of equations. The first thing I can do is solve this first guy, E inverse A, E inverse transpose Y equals E to the minus 1B. And then I can substitute X equals E inverse transpose Y. And the reason that I do that is I can solve the first one with conjugate gradient algorithm, and the second one is just a formula, right? So in principle, I've given you a reasonable set of steps. This is not a smart set of steps algorithmically because I need the Cholesky factorization of P. You guys get that? So basically, this is the same substitution that we used to prove the eigenvalue bound that I erased. Yeah. But here's the really magical thing. I can write down every step of conjugate gradient algorithm, but now essentially all that I do, let's go back to our steps. I'm sorry, my computer is so slow and we only have a minute left in class. Okay, here's our conjugate gradient algorithm. Every time I see A in these equations, I'm going to instead put in this thing, right? Because this is the new matrix that we care about. And every time that we see an X, I'm going to instead put in an E to the inverse transpose Y. And it turns out, and I'm going to let you do this at home because we're out of time. If you don't believe me, I can do it at the beginning of class next time. If you re-parenthesize that expression, you can keep getting products of E and E transpose. And a really magical thing happens, which is the following. That algorithm is actually equivalent to one that never needs E. In particular, this computer is the worst. Here's so here's that algorithm, right? So here all I've done is just put in the E matrix every time I'd had A. And now I'm going to make a few substitutions. And what I can get is an algorithm that never actually needed either one. It just inserts P in the right places in this code. And one thing you show is that these two things are exactly equivalent to one another. Like literally, like line for line. These are just different ways to parenthesize the same expressions. And the cool thing is this guy never actually needed a Cholesky factorization of P. Isn't that cool? So essentially, the whole point here, to summarize our strategy, we cook up a P that we think kind of looks like A inverse. In principle, we know that we could do CG on this matrix here from the Cholesky factorization of P, and what we've argued is that it'll converge even faster than if we'd somehow had to do it on the original product. And moreover, if we just parenthesize our expressions the right way, we never actually need access to Cholesky factorization at all. This is so cool. It is magic that this happens. And so basically, this is the same as conjugate gradient, just every once in a while you have a P kind of hanging out. Okay? There are all kinds of different choices of preconditioners. There's the diagonal one we kind of talked about. You just take the diagonal of your matrix and you do 1 over that, which at the very least oftentimes kind of kills bad covariance and statistical problems. You can like do things like take your matrix and then just like zero out entries that are close to 0 and compute the inverse. There's something called incomplete Cholesky, which is sort of the state of the art in a lot of simulation tools where you do Cholesky factorization, but every time you're going to introduce a non-zero in your matrix, you just skip that step. It's a weird heuristic, and it turns out to work really well. And there's all kinds of things that you can do in partial differential equation. So for example, maybe I'm solving a physical system, like I'm simulating heat diffusion, and I'm doing it on some big grid. I could do it on a grid which is 10 times coarser, and think of the solution of the heat equation on that coarse grid as an approximation of the solution on the big guy, right? This is called domain decomposition method. So then your preconditioner is like another PDE solver for a smaller version of the same problem. Isn't that cool? Right. So we're just about done with our discussion for today. Just to note really quickly, the beginning of our lecture made a baseline assumption, which is A is symmetric and positive definite. The natural question you should ask is, are there algorithms that don't have that assumption? The answer is yes, but they're much harder to derive. With the one exception, there's something called CGNR and CGNE, which are basically just the normal equations. So instead of AX equals B, they do A transpose AX equals A transpose B. And now it's positive definite, so now you can do it. But the only problem is you just squared the condition over. So you just like kind of negated the reason why you might use CG to begin with. And there are other ones out there. There's MinRes and GMRes, I think, are the most popular ones for generic matrices. And there are even versions of this that work for nonlinear problems. So actually, a competitor of this Adam algorithm that you see in machine learning a lot is to basically use the steps of conjugate gradient. And every time you see a residual, instead use the gradient of your function. And this thing is called, I think it's Fletcher-Reeves. It actually works pretty well. The convergence rate is pretty fast, but it's very hard to prove anything about it. Okay, folks, so with that, in our next lecture, we're going to talk about nonlinear problems again for one more lecture on optimization. And then finally, we will close this chapter, reset. You can forget everything we did, and we'll talk about interpolation problems. Okay, so with that, have a lovely weekend, and I will see you next week. Oh, and we have your midterm. So